I'd like to introduce Kelvin Long, from the editor of the Journal of the British Interplanetary Society, Icarus Interstellar, and the Institute for Interstellar Studies, to give his presentation and help set the stage for the rest of the discussions that we have today. All right, very good.
Okay, thank you. Okay, thank you very much. Really great to be here. Really proud of William. I met him and his parents last night. Really great story, so thanks very much for the story. Thank you also for Les and for the other team for organising this wonderful meeting. I've really been looking forward to coming here. I missed the first one, unfortunately, but I'm really glad to be here today. So I'm going to talk to you today about Interstellar. Really going to try and focus the discussions a little bit on the R&D, the technology, the starships, which is what we're really here for. And I'm representing really the Institute for Interstellar Studies, which I'll talk a little bit about later, also the JBIS journal, and of course also Icarus Interstellar, which is a non-profit foundation in the US, and some of the team are here as well. So Les Johnson set the stage a little bit with his discussion on how far Nashville is equivalent to getting to the stars. Our starships, if you can call them that, are really the Voyager and the Pioneer probes. That's the first thing that we have that is anything like a starship concept. Of course, they travel really, really slow, 17 kilometers per second, which is really, really slow, and something like 2 to 3 AU per year. Nearest star is 270,000 AUs away. So if you were to try and get there in 100 years, you have to go something like 2,700 AU per year, which is an enormous velocity, several orders of magnitude higher. Dr. Robert Forward was one of the pioneers of this subject, and he had this quote from one of his papers, which I really like, which I think nicely encapsulates the problem, which is that travel to the stars will be difficult and expensive. It will take decades of time, gigawatts of power, kilograms of mass energy, and trillions of dollars. Interstellar travel will always be difficult and expensive, but it can no longer be considered impossible. And I think that's really important because in previous decades, it was really part of the science fiction literature. And things have really been changing. And I'm hopefully going to give a little bit of a feel today for the rise of interstellar studies as a subject. And our task, I think, is to try and bring it into the mainstream so that we can pump some investment into the field. So we saw a lot of starship concepts earlier. Here's two really cool space art pictures from David Hardy, who's a British space artist. I believe the one over here is a fusion-powered vehicle. I'm not sure what propels this thing. But if you want to take a guess, please do. But they look really, really cool, so I thought I'd put those up. So there's a lot of engineers in this room. They recognize this, the X-33 Venture Star. And when you do aerospace engineering, as I did, you learn about the systems approach to aerospace engineering. You have your experts in materials technology, your structure, your propulsion, all your different fields. Now, to me, designing starships is no different to applying those processes. It's just what I call extreme aerospace engineering, okay? Because the environmental requirements, the constraints are much harsher. The velocities are much bigger, the energies are much bigger. You're traveling in space, which is a very cold environment, unless you're going near the stars. And the thermal loads on the vehicle. So this is the Project Daedalus study, which I'll talk a bit more about later. But I really think that the application of aerospace engineering to starships is something that is highly credible, and it's something that we can do. So let's talk a little bit about the requirements, and you'll probably hear a lot about that over the next 2 days. So I mentioned what it takes in terms of velocity to get to the stars. In terms of energy, you're talking about 10 to the 18, 10 to the 20 joules of energy, which is enormous. Power requirements of tens to hundreds of gigawatts, sometimes even greater. Costs billions to trillions. I've never seen an interstellar mission that's been costed for less than many, many billions of dollars. I mean, imagine trying to send something like a Voyager probe to the stars. What would that cost? Mission times, at least 50 years, and most of the concepts. If you want to go below that, you really need to push up from 50% of the speed of light, which is really difficult to achieve. Most of the concepts are centuries to get there. Cruise velocities, 2,000 to 3,000 AU per year. I compared that to the Voyager probes earlier. Exhaust velocities, getting into the thousands of kilometers per second, that's what you really need to be hitting. And accelerations are quite high as well. There's no point going over 1G if you've got people on board, because it starts to become uncomfortable. Distance, we're talking about really 4 to 20 light years as practical distances to travel to if you're going sub-light speed, unless you're going relativistic, such as an Bussard ramjet, which we'll talk about later. So an important distinction I want to make when we talk about starships, because you you talk to the media and the public, they say, is interstellar travel really possible? And you have to really define, what do you mean by interstellar? Are you talking about a probe that's the size of my pen? Or are you talking about something that's a world ship that's the size of the Isle of Wight in the UK? There's an enormous distinction about the type of starship or the star probe you're talking about. You also have to think about the type of probe, excuse me, in terms of, is it a flyby probe, is it a rendezvous probe, are you sending people? So each one of those has different requirements, and they become more harsher as you try to put people on board, as we heard from Jan Davis talking about how the astronauts have problems up in orbit. So the first thing we need to look for is energy sources, and it really does boil down to energy. And chemical just won't do the job. 13 megajoules per kilogram is completely insufficient. Any chemical rocket system is limited to about 5 kilometers per second maximum ISP, exhaust velocity. So that's not going to get you to the stars. And if you try and do that with chemical, you're talking about massive amounts of fuel, and there's just no point trying. So you go to the nuclear options, which are 1 million times more energy release. So there's nuclear fission, nuclear fusion, and there's some spin-off sort of exotic concepts such as fusion combinations and antimatter catalyzed fusion concepts. Very theoretical. The really big goal, I think, will be antimatter, because if you could create sufficient quantities of antimatter, you could really propel a spacecraft pretty fast, close to the speed of light. There are very exotic options such as vacuum and dark energy solutions, and of course propellantless solutions. We know about solar cells and laser cells, but there's all this talk about, warp drive. Is that possible, or is this something just to remain in Star Trek? My favorite method of getting to the stars is fusion propulsion, because I think it is viable. It's just, yes, we've been spending 50 years on the program. I read a paper the other day that talked about the peak amount of spending on fusion research since its entire history, and the peak only hit about $460 million in any year, which is about the cost of putting a shuttle in orbit, by the way. So the favored reaction for fusion is really, for fusion propulsion, is deuterium and helium-3, because then you get the protons out of there, which you can direct magnetically, and you haven't got to worry about such a large neutron flux, which radiates the surrounds. The problem, of course, is where you're going to get the helium-3, and we'll talk a little bit about it later. There are other options such as lithium-6 neutrons combinations and proton-boron combinations. My favorite option is the ICF route, which is really using laser beams, and this, of course, is what's happening at the National Ignition Facility in San Francisco. You take laser beams to implode a target, and you get to the hotspot conditions at the center, and then you get your self-sustaining fusion burn reactions. So you're depositing your alpha particles into the fuel, and this propagates outwards, and then you're getting your gain. Now, of course, NIF has been trying to achieve this for the last few years, and it's really an experimental program. It's had a few hiccups, and maybe if they carry on the campaign over the next few years, they might actually get there, and that would be really wonderful for science. So interstellar studies as a topic, I regard as really starting is in 1952. Prior to that, it was really science fiction. A lot of these science fiction ideas for, getting to the moon, for example, and Jules Verne and H.G. Wells, firing a big cannon, or Calverite paint, on a vehicle. Similarly, interstellar studies had a lot of very fantastic ideas. Les Shepard sat down and he said, okay, what does it actually take? And he wrote a paper, and he actually worked out what the energy is, what the mass ratio required, what the exhaust velocities are, and what sort of fuels you could use to get there. And this paper largely went unnoticed for many years. Les Shepard went on to also write lots of atomic rocket papers in the 1950s, which actually was the precursor to what later the US rover and NERVA programs, I think, really came out of those initial papers. And he also went on to found the IAF, which is a massive astronautical body in the world. So he wrote this paper, and it was published in JBIZ, which I'm the editor for. And JBIZ is also famous for the red cover issues. And there's a little photograph here. And between 1974 and 1991, we published quite a few issues of interstellar studies papers. And I think they are the golden standard, and that is our kind of, all of our key ideas from the interstellar community is in those papers, because you had a lot of studies going on at the time. It's really great to actually bring some of those red cover issues back. We've been recently publishing some of the 100-year Starship papers, so those are red covers. Let's talk a little bit about Daedalus, which is the only starship design in history, in my opinion. Okay, a really controversial claim for those who are really keen on starships. So when I say design, I have to qualify that, because a design to me is something that's gone through the concept, preliminary, detailed design phase, and you've looked at the subsystems and you've attempted to integrate them. Now, there were some contradictions in the design, because what they were doing was trying to balance being sufficiently credible and sufficiently bold. And they did this study in the 1970s, a 13-person team. And they did this in pubs, on beer mats, literally. Okay, they would meet every couple of weeks and have discussions. And what they did is they tried to combine current technology at the time with near-term extrapolated a few decades hence. So there are some contradictions in the technology, such as you've got AI probes next to vacuum tubes. Okay, but basically how it works is it's a two-stage engine design. So the first stage, you can see this huge reaction bell. And these are propellant tanks which have deuterium and helium-3 inside of them. The helium-3, 30,000 tons, was to be mined from the gas giant Jupiter, which suggests that you need a solar system-wide economy in order to achieve that. And it would have electron beams, and you can see this little graphic here. The electron beams would come in and hit the pellets as they were accelerated electromagnetically into the target. And this thing would burn these tiny pellets of deuterium helium-3 at something like 250 hertz pulse frequency. So every 1 second, 250 of these would be detonating. And the whole reaction bell would be expanding and recontracting to actually exhaust the plasma. So this is the first stage, and this would go for about the first 2 years. And then the tanks would drop off. The second stage would then ignite, another 2 years of burning. And then it would cruise to its destination, Barnard Star, in about 46 years. So it would get there 50 years later. Of course, it was only a flyby probe, so it would fly through Barnard Star in 4 days. And in that time, it was going to drop 18 subprobes, of which was 20 tons each. And it was going to do a whole lot of science, okay? So a really interesting design. It does have some design flaws in it. But for the 1970s, it was a really bold attempt. And what they were really trying to do was address the Fermi paradox. There's this contradiction between our expectations for life in the cosmos and our observations that we don't see any intelligent life. So what they sat down and said was, well, let's actually ask the question, is interstellar travel even feasible in theory? Let's see if we can conceive of a machine. And this is what they produced. And their conclusion at the end of the 5-year study was interstellar travel is feasible in theory, because if we can conceive of this machine at the outset of the space age, what could we do in 200 years from now? Just to give you some global scale here, this is Daedalus compared to some well-known buildings. Saturn V, of course, is at the rocket center around the corner, and I really enjoyed seeing that a few days ago. This is an enormous machine. It's 200 meters tall. The propellant's 50,000 tons total, with deuterium and helium-3, 450 tons payload mass. Okay? And it's just enormous. The structure is about 2,700 tons. So you can imagine trying to construct this in orbit. How many missions would you need just to put stuff up there? Clearly, it's not viable to do it by building it from Earth orbit. And what they would actually do was launch it from Cassini, and that's where they would mine the fuel from Jupiter. So you can see the Empire State Building compared, and you can see the St. Paul's Cathedral. I should point out these are done by Adrian Mann, who in my view is the modern day Chesley Bonestell stroke Ralph Smith. Ralph Smith was the British equivalent of Chesley Bonestell. And Adrian Mann's been working with a lot of the space organizations like Icarus Interstellar, and the British Interplanetary Society, the Institute for Interstellar Studies, companies like Reaction Engines, and all of the great artwork you're seeing coming out of these teams is due to this guy, Adrian Mann. So listen out for his name. In case you haven't got the scale just good enough, you can see here is the Tennessee Valley Interstellar Workshop people walking around the engine belt. So Les Johnson's future organizer will be hosting a tour of the Daedalus reaction chamber in centuries hence. So there have, of course, been other studies. Now, I said Daedalus was the only starship design. The Project Orion design was very much a design, but it was an interplanetary version. The only interstellar application of it was the 1968 paper by Freeman Dyson, where he talked about a momentum transfer interstellar version. But the actual design version, which was done in the 1950s and 60s, was on the interplanetary version. So the idea for Project Orion came out of Stanley Saul-Ulam and Cornelius Everett in 1946, and they wrote a paper a few years later. And they actually, later on when they had the program, which was Ted Taylor and Freeman Dyson and others, which was funded by General Dynamics and a few other organizations along the way, they did some experimental studies, and you can see the graphics here of the putt-putt test, where they put an explosive charge behind the pusher plate to demonstrate it. So how the Project Orion concept works is you can see the pusher plate here, you detonate nuclear bombs, maybe 100 meters behind it, and the products of this blast hit the plate and they push it, so the momentum is transferred. The absorption of the shock absorbers here takes that momentum, and the crew is sitting right at the front. Now, Freeman Dyson and others talked about going to Saturn within 7 years in this machine, and they were really planning for it, okay? They must be very disappointed. But it's the only thing we have which could get to the stars if you made an interstellar version today, if you could get enough of the fuel together. And Carl Sagan, in his Cosmos documentary, said he couldn't think of a better use for the world's stockpile of nuclear weapons than Project Orion. I should point out, by the way, that Project Orion is limited in terms of its velocity. If you use a basic atom bomb version, you're talking about 5% the speed of light, maximum theoretical. If you're talking about the hydrogen bomb version, you're talking about 10% the speed of light. So you're still talking about over a century travel time to get there, maybe 150 years. The best thing to do would be to go for a propellantless solution. So Daedalus carried its own propellant. We talked about 50,000 tons of fuel. Orion carried its propellant. It was like 300 tons of fuel and 100 tons of structure. This is the Project Bussard. Robert Bussard wrote his paper in 1960, and this one did get noticed, and it caused a lot of excitement at the time, because what it does is, instead of carrying its own fuel, is it travels through space and it mines the interstellar medium. So the interstellar medium might have a density of 100 to 1,000 atoms per centimeter cubed, something that's not really well characterized, and it depends on the diffusivity of the regions you're flying to. But there's a huge magnetic collector on the front. It's a bit like a Hoover, and it goes along sucking up all these charged particles. The problem is, how do you get these really fast protons that are coming into the front and collected on the surface? This has an enormous heating implications, because you're heating up the front, and you've got to moderate those protons. That's a theoretical problem, engineering problem to actually work out. The other problem with the Bussard ramjet is that you're actually generating a lot of drag because you're flying through the interstellar medium really fast. And so some of the calculations from Bob Zubin and others suggest that you may generate so much drag that it offsets any of that thrust that you can generate from the propulsion. So the current thinking is that the Bussard ramjet does not work. But if we can make it work, it solves the problems. And not only that, it can go relativistic, 99.99% of the speed of light. And there's a great science fiction book called Tau Zero by Paul Anderson, which is what the Tau Zero Foundation is named after. Paul Gilster's here today, which really explores an interstellar ramjet, and it actually circumnavigates the entire universe in the book. It's well worth reading. There have been other studies. Project Longshot was a US Naval Academy study in the 1980s by students, and it's not a bad effort, I must say. There's one report that goes into it all, and it was to go to Alpha Centauri. It was to decelerate, carrying a 30 tons probe, and it would also use fusion to deuterium helium-3. The only problem with the study is they said it would decelerate into the system, but they didn't allow for that in the actual design of the propellant, so it doesn't actually carry enough. So unfortunately, when they tried to put on the brakes, it wouldn't have stopped, and it would have kept going. But it's not a bad effort for a student study. Then you want to start thinking about human vehicles. So there is a concept called the Ensman Starship, which the guy who came up with the idea, Robert Ensman, claims he thought it in 1946, although it really started to emerge in the 1960s. And a few of us recently wrote a paper on the Ensman Starship. We spent a year and a half researching the history of it because it wasn't well characterized. And what it is, it's 30,000 tons of structure mass and 3 million tons of deuterium, which will be mined from the gas giants, which is this huge sphere at the front. And you can see the habitat structures, which are three sections to it. And the idea is you travel to the stars. They always travel in twos. And Harry Stein wrote an article in Analog in 1974 where he talked about a whole program of interstellar exploration, sending 10 of these vessels, which could have been launched around the year 2000. And they would get to the nearest stars, they would explore the system, and then they would move on to the next system. But these are really fanciful ideas. And Harry Stein talked about it going at 30% of the speed of light. That's not possible with fusion propulsion. So you really talk about 9% of the speed of light, which is what Robert Ensman is actually claiming. But this is one of the ways you could do it. Then you want to go to the world ship concepts, which are these large, massive scale vehicles. So this thing is 200 kilometers across, 20 kilometers diameter. So Alan Bond and Tony Martin, who also did the Daedalus studies and also run the company Reaction Engines, looking at Skylon, they did this study in the 1980s, and it was published in the Jabi's Red Cover issues. This is, again, one of the Age of Man images. They didn't have the sophistication to produce these sorts of images back in the 80s. But basically, it would carry thousands of people. So it's a bit like an O'Neill cylinder strapped with a propulsion engine at the back. Notice this long column towards the rear. This is an ocean inside of it. Okay, so this is an ocean-going vessel. And this would travel to the stars, and it would just be maybe 3% of the speed of light, and it would just be traversing the entire galaxy, going from system to system. So really visionary concept. And they did all the calculations for this, a lot of the calculations. So, of course, before you can even think about trying to build something like a world ship, you need to think about how to actually do it, how to assemble it. And the biggest problem for Interstellar is getting cheap access to Earth orbit. because if you're going to try and do it on shuttles and it's costing $400 million per launch and tens of thousands of dollars per kilogram to get there, it's just not sustainable. What would it take to assemble something like Daedalus, with its thousands of tons of mass? So SSTO is, in my personal view, the way forward to solving that. If you can crack the technology problems, single-stage to orbit vehicles can get you there cheaper. But also it opens up the entire solar system, so you can go on and mine the asteroids and do other things. And then you can start to build your solar system-wide economy. And that's when interstellar civilization starts to really begin. This is the Skylon spaceplane from Reaction Engines. And it's really exciting because they've been working on the heat exchanger problem for the last 20 years, and they claim to have cracked it, which means that you can launch these things on a rocket mode at very high altitude and get into space, and landing on a single runway. So we mustn't forget that there are other ideas out there, and Robert Forward was one of the pioneers of Interstellar, and he was really keen on propellantless solutions. He didn't like the idea of carrying propellant, and one of the things he came up with was microwave beam propulsion, and there's a few people here that are quite keen on that idea. So microwave beams are a bit like lasers, so they're masers, but the idea is that you have a huge Fresnel lens zone around the Earth orbit, and you're talking, this thing's about 50,000 tons. Note that's similar to the mass to propellant of the Daedalus probe. And you have maybe a 1-ton payload, and you just microwave, you get the solar collector from the sun, and you push a microwave beam which accelerates up to about 20% of the speed of light, which will get you to the stars reasonably quickly. So the good thing about these sort of microwave beam concepts is you can potentially launch very small payloads, so you could get to the stars much more quicker. But you still need to build these large structures. I can't go forward without at least talking about Star Trek and breakthrough propulsion physics. One of the issues we have in Interstellar is managing that distinction. I organised a conference in 2007 in London, which was dedicated to warp drive, because in 1994, a chap called Miguel Alcubierre published a paper where he explored the idea of a warp drive metric using general relativity. And it was the first time someone actually tried to look at the problem. So we had a conference and we discussed all of the progress to date on warp drive, and it was quite a visionary conference. Richard Abusi was there, who's here today, and Cardi McConey came along, and it was a really great event. And we kind of spent some time thinking about all the problems that there are, and I think I came up with 19 engineering and physics problems to actually make the warp drive a reality. At the time it looked completely impossible. And it's really interesting to see the progress that's being made today by some of the team who are still working on warp drive, and they're now claiming incredible small amounts of negative energy in order to get the thing to work. So breakthrough propulsion physics sort of concepts is what we call technology readiness level 1. And I think it's really important that while we're trying to work on the more practical solutions, we also keep an eye on the breakthrough propulsion technologies. And that's why I was really sad when the NASA breakthrough propulsion physics program was closed down, because I think that was an excellent program which Mark Millis was leading. And it would be good to see the NIAC doing some of that sort of breakthrough propulsion work. So 1952, interstellar studies really started as an academic topic. People started to look at it more rigorously. Since then, we've had a whole load of books published. Okay, so Greg Matloff has been one of the pioneers, Paul Gilster's Centauri Dreams, and there's been a few others. Les Johnson's Going Interstellar is the most recent. Eric Davis and Mark Millis published their book Frontiers of Propulsion Science a few years ago, which is an excellent book looking at the literature. I've got my own book at the end, which I wrote. Notice I've got it bigger than all the others because I'm trying to flag up my own book. So that was a lot of fun writing, but it became stressful towards the end. And I really wrote it to teach myself about the broad range of subjects and also trying to communicate some of the ideas to the public. What really gets me about Interstellar is you've got all these pioneers that work in this field, okay? I mean, some of the names you'll recognize. Les Shepard I talked about, Arthur C. Clarke, Robert Bussard, Robert Ford, Carl Sagan, Greg Matloff, Jeffrey Landis, Alan Bond, Mark Millis, Freeman Dyson, and Jim Benford. All great, really great people. And what really amazes me is a lot of these people are trained physicists or astronomers, and they have a mainstream job, and yet they're going home in the evening and they're thinking about interstellar travel, or they're thinking about the search for extraterrestrial intelligence. And it sounds crazy, right? And the good thing about Interstellar is there's lots of people on our subject which haven't even had a scientific training, but they're working on stuff and they're generating stuff which is of really good value. And that's the thing about JBIS, it's always been open to receiving publications from the amateurs, if you like, if their papers are rigorously produced. And there aren't many other fields that are as open as Interstellar. So it really gets me that these people are working on this stuff. Have we really got 5 minutes?
That was 5 minutes ago.
Oh.
I'm sorry if you can. We'll go a couple more minutes and then we'll have a break.
So I started at 22, was it?
We'll just keep going.
Okay. I'll accelerate because I haven't talked about the Institute. Okay. So in 2009, we launched Project Icarus, which is to revise the Daedalus design. And I won't have time to talk about that. But that's something that a lot of the guys are still involved with, trying to come up with a revised model for a starship design. Out of that study, I started to look at the idea of forming an institute for interstellar studies, and that was really as a response to the DARPA initiative. And I identified a whole lot of things we need to do, such as capturing the knowledge that's been done to date, getting research support into the community, generating designer capabilities so that people can actually do the calculations, producing blueprints, because we only have Daedalus as the one design starship, developing strategic and technological roadmaps, the scientific tools. How many codes are there, design codes in Interstellar? None. We need actual codes to do the numerical analysis. Experimental validation, where's the experiment? We need to really get our act together as a community and start to push all this. I haven't got time to talk about this. So the Institute for Interstellar Studies was formed in August of last year, and it was really to try and catalyze on the achievements to date. This is our logo. And this is our mission statement and our vision statement. And really, there's three main arms to the Institute, which is education, research, and enterprise. So we want to get the students to try and train them up and help them to generate the capability so they can do the work. Then we push them into the research so they can produce the papers and the design solutions. And then we're going to look for spin-off applications in terms of patents and technologies, which we can push. So we've got 8 boards of directors involved. I'm going to have to go through this quickly. We've got a senior advisory council, some big names there, including Freeman Dyson, who's kindly joined us. Claudia McConey is also one of the members. We've got loads of consultants, including Alan Bond, who worked on the Daedalus project. We've got about 70 people in the organisation to date. We've got a website, which is i4is.org, so please visit it. We've got another website called the Interstellar Index, which attempts to knowledge capture everything that's been done to date, including every single paper that's ever been published on Interstellar. We've got a newsletter called Principium, which is really trying to represent the entire community. I've given the editor, Keith Cooper, the briefing to not just represent the Institute, but to represent everyone, so that we can work together. A little bit about the business model of the Institute. So what we are is, I mentioned the research and the development and the enterprise. What we want to try and do is to spin off some of the R&D that we're doing as for-profit companies. So we're actually going to help people, and if they've got a technology and a patent, and we already have some patents in the Institute that people have developed, that they own, and they're willing to give to us. And we're going to try and spin them off as for-profit companies, and then they're going to own it. So we're not going to interfere, but we're going to write a contract so that we can get some benefit from that. And what I also did is I put a company together called Stellar Engines in March of last year, which has the job of trying to underwrite and support a lot of the Institute's activities. So I'll just go through this quickly. We've got a whole load of projects. I won't be able to talk about those today. We've got 10 at the moment, and they're really innovative, going from the very practical to really visionary breakthrough propulsion type concepts. And I want to point to the Stanford University model in the 1940s, where the Frederick Terman, the Dean of Engineering, encouraged a lot of the graduates to go off and produce their own companies. And this is what really produced Silicon Valley. So that's kind of the model that we're trying to develop. And these are the projects, and I can't talk about those because we ran out of time, and Les would be very unhappy with me. But basically, we're looking at things like black hole propulsion research. We're looking at quantum neurogenic computing. We're looking at Sentinel, which is the search for extraterrestrial intelligence as a way of solving the Fermi paradox. We're looking at generating negative energy sources, gigavolt electron lasers. And we're also looking at using CubeSat technology to actually help to validate some of the architectures for interstellar design concepts, such as propulsion. So what can you do with a microwave beam propulsion on a cube-scale architecture, for example? And this is my last slide, and I've ended with the well-ship concept, and something, a quote I really started to learn about from William Harmon a few years ago, which I think is a really nice quote, and something which I think can't be said enough for this community, is that space exploration must be carried out in ways as to reduce, not aggravate, tensions in human society. And so often, what happens in our community is people become competitive or the personalities clash, and it's really important we get over that, start to work together. And I'm really pleased to see this meeting that everyone's really positive about trying to work together to get something actually achieved in Interstellar. So thank you very much for listening, and I'm sorry about the rush.